This video is about factograph sparsification in visual odometry for lava tubes exploration. The context of this research is robot navigation for space exploration. The challenge here is to navigate in an underground context with cameras and onboard illumination. We validate our solution on both real and simulated data. To lower the computational cost of our system, we focus on the optimization of our problem. We use the factograph representation to illustrate a sliding window visual odometry. We have here a fixed number of robot states and only visual constraints between robot poses and landmarks. When we reach the boundary of the window, we marginalize the first frame and the isolated landmarks using all the factors in the Markov blanket that is represented in blue. We obtain a prior that links all the variables that were in the Markov blanket. The resulting factor is dense and may break the sparsity of our SLAM problem. To recover it, we can turn this dense factor into a set of factors. Different topologies can be used to represent the prior. On the left, the landmark tree, and on the right, the absolute topology. But which topology is the best? To find it out, we compare them using the same measure that we use to compute those topologies, the KLD. In the end, we selected the landmark tree, using off-diagonal blocks of the information matrix to find the most informative tree. Here you can see an example of our visual odometry on our simulated dataset on a planetary surface. You can see on black the marginalized landmark. In green, you can see the sliding window. We use this dataset to perform KLD comparison. Let's move on some real data. This is the mine environment from the OIVO datasets. Our visual odometry is able to produce sparse maps that illustrates greatly this mine environment. Finally, here is the tunnel from the OIVO datasets. We precise here that our odometry runs at 100 Hz, which is suitable for real time. Here, we can observe that there is extreme lighting conditions.